Hello and welcome to the last lesson on factoring and also the last lesson of Unit 7. So we're going to be doing factoring special cases. So hopefully today you'll be able to identify and factor a polynomial that is a special case. Now I want to point out right away that this lesson, you don't really need to know it. It's not required for you to know these special cases. It will make things easier if you can identify them though. So especially special case number one. Special case number two, you kind of have to know that one. Special case number one, you can kind of get by if you don't know it. Well, let's take a look. You notice that A is not 1, it's 4. So like we did in the last lesson, we look for a GCF. Is there a GCF here? No, there's not. Okay, so what do? We want to find factors of 36. Where's 36 come from? 4 times 9. That add to 12. Well, hopefully you see that that's 6 and 6, right? So then I'm going to split this up, 4x squared plus 6x plus 6x plus 9. And now I'm going to find the GCF of the first two terms, which is 2x. Divide 4x squared by 2x, and I get 2x. Divide 6x by 2x, and I get 3. Second one has a GCF of 3. 6x divided by 3 is 2x. 9 divided by 3 is 3. And then we rewrite with the first two terms, the two GCFs. I get 2x plus 3 times 2x plus 3, and the two factors are identical. That's what makes it a special case, okay? I could rewrite this as 2x plus 3 squared since they're the same, okay? So what do you notice about the two binomials? They are the exact same, right? That's what I want you to see. Now, there's some things about this that can help you move a little quicker. Look at the original polynomial. So, oops. Oops, sorry. A little weird on me here. What do you notice about the last polynomial? Or the original polynomial? The first and last terms. Well, 4x squared is a perfect square. I can take the square root of 4 and get a good number. Same with the last term. The square root of 9 is 3. Right, so I'm going to write what I had for the answers here again, so you can see kind of what happens. Okay. The other thing is they're both positive. Okay. So if you have a perfect squares as the first term and the last term, I don't care about the middle term really, but if the first term and the last term are perfect squares and they're both positive, this might be a special case. I said might be. If the first and last terms of a polynomial are perfect squares, then the polynomial is a special case. That is not always true. It might be true, but it's not always true. This is why it's a good idea to check. You actually have to check to make sure. If you think that it's a special case, especially special case number one, you want to check to make sure that when you FOIL it back out, you get 12x when you do. So I'm going to check 2x times 3 is 6x. 3 times 2x is 6x. If I add those together, I get 12x. And it does work here, but it won't always work. And I'm going to give you an example of that here in a little bit. So let's try a few practice problems with this. So number one, you see that the first term is 9x squared. The second term is positive 25. So it might be a special case. So let's try it. What's the square root of 9x squared? It's 3x. What's the square root of 25? It's 5. So I'm going to do that again here. Now, they have to add to get negative 30x. So they have to add to get negative 30. That means they both have to be negative. Okay, they have to be the exact same if it's a special case. Now, let's see if it worked. I'm going to multiply the outer terms. 3 times negative 5 is negative 15x. And the inner terms, that's negative 15x. I don't need to check the first terms and the last terms because we got those by taking the square root. We know that those give me 9x squared, and we know that -5 times -5 gives me 25. Well, -15 plus -15 is -30x. Is that what we wanted in the middle? Yes, it is. So that is my answer. So right there, 3x minus 5 times 3x minus 5 is my answer. Now, like I said at the very beginning, if this does not make sense to you, just do it the old way. Do 9 times 5, you get 225. What two numbers multiply to 225 and add to -30? It'd be -15 and -15. You do the grouping, and you should get the same answer. Now, let's keep going just to make sure that you understand this. So 16x squared is 4x and 4x. Square root of 1 is 1. And then they're both positive because the middle term is positive. That's another thing that you can see. The sign has to be the same as the middle term if it's one of these special cases. All right, so let's check it. 4x times 1 is 4x. 1 times 4x is 4x. That gives me 8x. Is that what I wanted? No, I wanted 10. So this one is actually not a special case. So we need to start over. There's no GCF. Do 16 times 1. I need two numbers that multiply to 16 and add to 10. Well, hopefully you can get that pretty quick. That's 8 and 2. So I'm going to rewrite this as 16x squared plus 8x plus 2x plus 1. Notice what I'm doing here. The special case didn't work. That's why it's important to check. If it doesn't work, you need to go back and do it the old way. So the GCF of these two is 8x. When I divide, I get 2x plus 1. 2x plus 1, the GCF is just 1. Divide by 1, nothing changes, so it's 2x plus 1. So the two binomials are 8x plus 1, 2x plus 1. Done. All right. Next one. Well, hopefully you see that 3 is not a perfect square. If I take the square root of 3, it's not going to give me a good number. So what do? Well, I go the old school way. What I did last lesson. First thing I'm going to do is I'm going to check for a GCF. Is there one? Yes, there is. I can actually take out a 3 on each of these. So when I do that, I get x squared plus 8x plus 16. Don't forget the GCF goes down here. Now I got an easier problem because a is 1. Two numbers that multiply to 16 and add to 8, it's 4 and 4. This is actually a special case because the two binomials are exactly the same. But I didn't have to go through the whole checking process because I know that 4 times 4 is 16 and 4 plus 4 is 8. So we're good. That's done. Okay. Last one on the front here. Let's say I don't like the special case. Let's say I'm multiplying 81 times 4. There's no GCF here. So I'm going to multiply 81 times 4. That's 324. That's a big number. If you're thinking, oh my goodness, it's a huge number, it's probably going to be a special case. If you get a huge number like that, that means the two numbers have to add, two numbers that multiply to 324 and add to -36. That's -18 and -18. The fact that those two factors are the same, that's what makes this a special case. So I'm going to write this as 81x squared. So I'm showing you this because I want you to see that when you get a huge number like that, your first thought should be special case. GCF here is 9x. 81x squared divided by 9x is 9x. -18x divided by 9x is -2. GCF of -18x and 4 is -2. Divide by -2, I get 9x. 4 divided by -2 is -2. And I get 9x minus 2. 9x minus 2. And you can see that it is a special case. Square root of 81, x squared is 9x. Square root of 4 is 2. Sign is the same as the middle term, just so you can see that the shortcuts could have worked there. Okay, so that's special case number 1. Hard to identify sometimes and important to check. Special case number 2, much easier to spot. way easier to spot. So let's take a look at it. What's different about this one? The middle term cancels, right? 9x squared minus 16, there's no middle term. And the last term is negative. That's a big one that you want to see. Okay. For this to happen, okay, the first terms of the binomials must have, the last terms, not the first terms. The last terms of the binomials must have the same number with opposite signs. Right? The only way for these two things to cancel is if the first and the last terms are like 4 and -4. 4 times -4 gives me -16. 4 plus -4 gives me 0, which means the middle term is going to cancel. All right. So when you have this situation, you have to be a special case. Notice how both the first and last terms, again, are perfect squares. In fact, you'll see some people call this the difference of squares because you're subtracting two perfect squares. The answer to the above question, what's the square root of 9x squared? It's 3x. Square root of 16 is 4. 3x and 4. Now, unlike the front, you have to have opposite signs. They are the exact same except for the signs. And if you FOIL that back out, you'll see that you get 9x squared minus 16. All right, so let's do a couple more practice. These are a little bit quicker. Okay. And there's no question, this is definitely a special case because the middle term cancels. Square root of 49 is 7x. Square root of 1 is 1. So 7x plus 1, 7x minus 1. When you see this special case and you understand it, it goes very, very quickly. Okay. Number 2, a lot of people go x plus 5, x minus 5. FOIL that back out, see what you get. That is not right. It's got to be subtraction. Because of this plus, this one can't factor. I wanted to put that in there because I want you to see that it's got to be a difference or subtraction between the two terms. If it's plus, it can't be factored. All right. Number 3, those are not perfect squares, but I do have a GCF. Still have that in play here. The GCF on this one is 3x. So if I divide by 3x, I get 4x squared, or sorry, 4x squared. 3x divided by 3x is -1. GCF goes in the line, and now I've got my special case. Square root of 4x squared is 2x. Square root of 1 is 1. Same numbers, different signs. Done. Last one. Pause it. Try it. Hopefully you're getting this. Hopefully it's clicking. 10x plus 9. 10x minus 9. All right. I want to reiterate before I end this that if you didn't understand these special cases, you could have just factored these like we did in lesson 7. However, if you are able to identify the special cases and you understand the shortcuts, they can be done very quickly. So it's kind of a tool that I'm adding to your tool belt that you may not use, but if you know how to use it, it can be very helpful. So that concludes lesson 8, and that concludes our whole unit.